What if the universe isn't telling us the whole truth? We've been taught that nothing can move faster than light, that it's the ultimate speed limit baked into the fabric of space and time. But some equations whisper otherwise. They suggest the existence of a particle so strange, so fast, it doesn't just outrun light. It may even outrun causality itself. This particle is known as the tachyon, a concept born from the mathematics of quantum field theory and special relativity. Tachyons travel faster than light. In fact, they only exist beyond this cosmic speed limit. And because of this, their behavior turns everything we know about time upside down. Tachyons don't move from past to future. They move backward in time. They arrive before they leave. They cause effects before causes. No experiment has directly observed a tachyon. But despite this, the idea persists, like a shadow just beyond the reach of observation, lurking at the edge of our theoretical frameworks. And if tachyons are real, then time, motion, and causality, the very pillars of physics, might not be as fixed as we believe. To truly understand why tachyons could exist, we must go back over a century. In the early 20th century, Einstein's theory of relativity introduced the concept that nothing could exceed the speed of light. As an object with mass accelerates, its mass increases. At light speed, the energy required becomes infinite. Therefore, no massive object can break that limit. But what if a particle never needed to slow down? What if it was born faster than light? In 1962, physicist Gerald Feinberg proposed a particle that could exist only at superluminal speeds. In his model, the tachyon had imaginary mass, not imaginary as in made up, but imaginary as in a number multiplied by the square root of 1/1. This idea might seem absurd, but in physics, imaginary numbers aren't fiction. They're used in wave equations, quantum mechanics, and even in electrical engineering. Tachyons are not supposed to be detectable in the normal sense. Instead, they appear as mathematical artifacts in quantum fields. They're not real in the traditional sense, but their existence could signal instability in a field, prompting it to evolve to a more stable configuration. In string theory, the appearance of a tachyon means the vacuum state is unstable. The universe wants to roll into a more stable shape. In this sense, tachyons may not destroy physics. They may help refine it. But here's where things get wild. If a tachyon could carry information, it would allow communication backward in time. This violates the principle of causality, the idea that causes precede effects. If you could send a message to the past, you could warn yourself of danger or cause paradoxes. Like the grandfather paradox, what if you prevented your own existence? That's why many physicists are cautious. Most theories that include tachyons carefully limit their effects so they can't transmit usable information. They're often called virtual particles, part of internal processes in a quantum system that can't be directly measured. Still, the idea refuses to vanish. Tachyons appear in speculative physics, in some versions of brain cosmology, and even in theories trying to explain dark energy or the inflationary period of the early universe. And for science fiction, tachyons are everywhere. From Star Trek to Doctor Who, tachyons have been used to explain time travel, cloaking devices, faster-than-light communication, and paradox resolution. But even though no real experiment has yet proven their existence, tachyons continue to provoke, forcing physicists to question the very structure of time and space. Are they real? Or are they simply a symbol, a hint that something bigger, stranger, and more beautiful lies just beyond our current understanding? In the end, whether tachyons exist or not, their ghostly presence reminds us of a vital truth. The universe may still hold secrets beyond the light. The one law older than physics itself is this: reality must make sense. Before Einstein, before quantum mechanics, before the discovery of atoms, Humans believed that effects followed causes and time moved forward. But tachyons challenge that very foundation. These hypothetical particles, born from math, not observation, ignore our rules. They don't just move fast, they move backward through time. And here's the twist. If they exist, they may not just bend the laws of physics. They could point to an entire hidden layer of reality. Let's dive deeper. Einstein's special relativity hinges on one unbreakable limit: the speed of light. For any particle with mass, moving faster than light is impossible. That's because as you accelerate, your mass increases. To hit the speed of light, you'd need infinite energy. But tachyons aren't massive in the traditional sense. In fact, their mass is imaginary, a concept that comes directly from solutions to the equations of motion when speed exceeds light. Mathematically, this isn't nonsense. Imaginary numbers are used all the time in wave mechanics, electromagnetism, and quantum field theory. In those equations, a tachyon is a solution that appears when the energy of a system isn't minimized. A signal that something deeper is going on. Imagine the universe as a landscape, full of valleys and hills. A field that contains a tachyon sits atop a hill, an unstable point. It wants to roll down to a more stable state. In this way, tachyons don't just break physics. They reveal when it's incomplete. That's how physicists interpret them in modern theories. Tachyons aren't necessarily real particles. They're indicators, clues. They show up in unstable vacuums, or when a theory isn't in its lowest energy configuration. In string theory, tachyons indicate that the chosen vacuum, the background geometry of space-time, is unstable. Once the tachyon condenses, the vacuum evolves to a more stable form. So the presence of tachyons doesn't signal chaos. It signals transformation. This has led some to propose a wild idea, that the universe we experience today, with stable matter and consistent laws, is the result of tachyon condensation, a kind of cosmic phase shift. Think of it like this. Just as water turns to ice at a certain temperature, perhaps the early universe froze into stability when the tachyon fields settled. But even more fascinating is what this implies for hidden dimensions. In theories like superstring theory or M theory, there are more dimensions than we can see, sometimes 10 or 11. Tachyons may live in these dimensions, invisible to us, but still affecting the structure of space-time. Some physicists think tachyons may be connected to brane theory, the idea that our 3D universe is a membrane floating in a higher dimensional space. Tachyons could be vibrations in these extra dimensions, hinting at interactions we cannot yet observe. If true, this opens up the possibility of parallel universes connected by quantum fluctuations and tachyon interactions, a multiverse where causality is not fixed and time can flow in strange loops. But what if tachyons can be more than just messengers of instability? In some bold theories, physicists explore whether tachyons could be real particles, not just mathematical warnings. If they exist and can interact with normal matter, they might be detectable, perhaps in high-energy cosmic rays or in quantum field disturbances. But here's the problem. Allowing tachyons in a theory usually breaks causality. That is, if you can send a tachyon message, you can send it backwards in time. Imagine receiving a message before it was sent. That leads to paradoxes, like telling your past self not to make the mistake that led to the message in the first place. Physicists solve this by restricting tachyons to be virtual. They can appear in calculations, but can't carry usable information. Still, some fringe physicists suggest that a hidden sector of the universe might allow tachyon communication, but only under special conditions, such as near black holes or in regions of extreme space-time curvature. Others wonder whether entanglement, one of the strangest features of quantum mechanics, might be tied to tachyon-like phenomena. In entanglement, two particles can be instantly correlated, no matter how far apart they are, a behavior Einstein called spooky action at a distance. Some interpretations hint that hidden, faster-than-light influences might be at play, and perhaps tachyons are the unseen hand guiding this connection. The idea is speculative, but in the search for a unified theory of everything, no possibility can be ignored. Whether they are real or not, tachyons push us to confront questions we often avoid. What is time, really? Is the future already written? Can the past be changed? Is causality a law, or just an illusion born from limited perspective? Tachyons may never be found in a detector, but their presence in the equations of physics and in the minds of those daring enough to question everything keeps the dream of deeper truths alive. Perhaps someday, with better instruments or new insights, we will catch a glimpse of that hidden layer and understand that reality is far stranger and more fluid than it seems. In the eyes of quantum field theory, the vacuum isn't empty. It's alive, seething with energy, fluctuations, and possibilities. What we often imagine as nothingness is actually a churning foam of virtual particles popping in and out of existence. And among these virtual specters may hide the most elusive and controversial of all: tachyons. The quantum vacuum is not calm. Even in the absence of matter, it contains the potential for everything, a background hum of probability and uncertainty. According to modern physics, particles are simply vibrations in quantum fields. The electron, for example, is a ripple in the electron field. Photons are ripples in the electromagnetic field. So, what happens when a quantum field becomes unstable? It tries to find a more stable configuration. This process is known as spontaneous symmetry breaking, and it's often accompanied by strange signals in the math. One such signal is a negative squared mass, the defining feature of a tachyon. This doesn't mean the particle is literally imaginary. It means the vacuum state is unstable, like a marble sitting atop a hill, ready to roll into a valley. That roll is called tachyon condensation, and it's how fields find stability. In the 1970s, when string theory was being developed, physicists found that some string models naturally predicted tachyons. At first, this was seen as a flaw, a bug in the theory. But over time, researchers realized that tachyons could signal a transition from one vacuum state to another. This is similar to how water vapor condenses into droplets, a phase shift. The presence of tachyons, then, wasn't a problem. It was a clue to how universes might evolve. One of the most famous places where this idea comes into play is in bosonic string theory. This early version of string theory had a tachyon in its spectrum, which led scientists to explore whether this indicated an instability in the space-time it described. It turned out that once the tachyon condensed, the system rolled into a more stable vacuum, and new possibilities emerged. In this context, tachyons are not travelers. They're triggers. They don't necessarily exist as particles zipping around faster than light. Instead, they exist as signals in the equations, indicators that a transformation is about to happen. But that doesn't make them any less mysterious. If tachyons are connected to vacuum instability, could they be tied to the early moments of the universe? Some theorists believe that the very birth of our universe, the moment of cosmic inflation, might have involved tachyonic processes. The vacuum, unstable and super-energized, exploded outward, expanding faster than light itself. In fact, inflation theory requires fields with negative pressure, a key feature of tachyonic behavior. And perhaps, as the universe expanded and cooled, tachyon fields settled, locking in the laws of physics we know today. But what if some of those fields never fully stabilized? What if remnants of tachyonic energy still lurk in the structure of space-time? Could they be driving dark energy, the mysterious force accelerating the expansion of the universe? Some models suggest that tachyon fields could provide a candidate for dark energy, a slow-roll field whose energy never quite dissipates. This would mean the fate of the universe is still being influenced by a field born in chaos, a ghost of instability, guiding galaxies ever farther apart. But there's another possibility, that tachyons appear not just in cosmic beginnings, but in black holes. The region near a black hole's event horizon is a cauldron of warped space-time. Some physicists speculate that under such extreme conditions, vacuum states might again become unstable, and tachyonic fields could emerge. If this is true, then black holes could be gateways not just to destruction, but to transition, points where space-time itself reconfigures, where new universes could be born. This ties into the idea of cosmic censorship and the information paradox. If tachyons exist near singularities, they might play a role in information conservation or in spawning baby universes. But even if these ideas remain speculative, they offer a tantalizing glimpse into the deep fabric of reality. Tachyons, in this sense, are not merely fringe physics. They are mathematical beacons, guiding us through the fog of quantum uncertainty toward a more complete theory of everything. A reminder that the vacuum, that supposed emptiness between stars, is anything but empty. Instead, it may be the most dynamic and creative realm of all. So, the next time you stare into space and think you're seeing nothing, remember, you're looking at the birthplace of possibility. And somewhere in that quantum sea, the ghost of a tachyon may still be dancing. In the 1970s and 1980s, theoretical physics was reaching for something grand, a unified theory of everything. At the heart of this quest emerged a radical idea. All fundamental particles are not points, but vibrating one-dimensional objects called strings. And so, string theory was born. These strings could vibrate in different modes, giving rise to the different particles of the Standard Model, photons, electrons, quarks, as well as to gravitons, the hypothetical carriers of gravity. It was beautiful, elegant, a framework that could unite quantum mechanics with general relativity, two pillars of physics that had never fully agreed. But there was a problem. In the early versions of string theory, particularly bosonic string theory, physicists kept encountering a disturbing mathematical anomaly. The theory predicted the existence of tachyons. Not virtual hints or symbolic signals, but actual, faster-than-light particles embedded in the fundamental spectrum of the theory. This created a dilemma, because tachyons in this context implied instability. The ground state of bosonic string theory wasn't stable. It was perched precariously on top of a potential energy hill. And like any unstable system in physics, it would want to roll down into a more stable state. So what did that mean for string theory? Was it fundamentally broken? For some time, this was a serious crisis. Many physicists began to doubt whether string theory could describe reality if it demanded particles that violated causality and undermined the very fabric of time. But as with many scientific revolutions, this apparent flaw became a window into deeper truth. The tachyon was telling them something. In this view, the presence of a tachyon in bosonic string theory was not a bug, it was a clue. It meant that the version of space-time being used, the dimensional structure, the vacuum state, was wrong or incomplete. The theory needed refinement, and so came supersymmetry. Incorporating supersymmetry into string theory, which pairs bosons, force-carrying particles, with fermions, matter particles, helped remove the tachyon from the spectrum. This led to superstring theory, a more stable and mathematically robust framework. Now, with supersymmetry, 5 different versions of superstring theory emerged, each consistent in its own way, and none featuring unwanted tachyons in their low-energy states. But this raised a new puzzle. If there were 5 different consistent theories, which one described our universe? The answer came in the mid-1990s with the rise of M-theory. This mother theory suggested that all 5 string theories were actually different aspects of a deeper, 11-dimensional framework. The tachyon crisis had helped spark a chain of theoretical upgrades and brought physicists closer to a unified vision. But even with tachyons removed, they didn't disappear from the conversation. In fact, in certain conditions, particularly involving D-branes, higher dimensional objects in string theory, tachyons still emerge. These tachyons indicate that a configuration of branes is unstable and will decay into a more stable arrangement, similar to radioactive decay in nuclear physics. This leads to the concept of tachyon condensation on D-branes, a process through which unstable brane structures dissolve or morph into lower dimensional states. In a way, tachyons became tools, not threats. They help physicists understand which configurations of space, strings, and branes are physically viable, and which are doomed to decay. But they also hinted at something else, that the universe might be more dynamic and flexible than we ever imagined. Rather than being static, space-time, and the objects within it, might constantly evolve through hidden processes driven by field instability. Tachyons in this light aren't violations of physics. They're instruments of cosmic refinement. In some versions of string cosmology, it's believed that our universe might have started as a tachyonic field collapsing from instability. The Big Bang, in this view, could have been a phase transition, the resolution of a tachyonic state into a stable, expanding universe. This is a radical but compelling idea, that the ultimate engine of cosmic creation wasn't stability, but instability resolving itself. And perhaps the tachyon, this once-feared ghost particle, is the mathematical fingerprint of that transition. Even today, tachyonic states are used as test beds in simulations and as probes into the mysterious string landscape, a vast space of possible vacuum configurations allowed by string theory. Each vacuum has its own physical constants, laws of physics, and particle spectra. Some may have tachyons, others may be perfectly stable. We happen to live in one that seems stable, but are others out there? Are tachyons still lurking in unreachable corners of the multiverse? Or are they still active in our own universe, guiding unseen processes in dimensions beyond our perception? No one knows for certain. But what is clear is this: without the tachyon, string theory would never have evolved into its modern form. It forced physicists to question assumptions, abandon broken models, and imagine a universe where time, space, and matter arise from vibrating strings and higher-dimensional membranes. And perhaps, just perhaps, the tachyon still has more to teach us. Imagine watching a glass fall from a table, shatter, and then the shards leap back together, rise, and land perfectly whole. Absurd, right? That's because our experience of time is linear. But what if that's an illusion? What if causality, the rule that cause precedes effect, isn't absolute? What if it's possible, at least theoretically, for effect to precede cause? This is where tachyons re-enter the story. Tachyons, by definition, are particles that always move faster than light. But in the framework of special relativity, something strange happens when you imagine such a particle. From certain perspectives, a tachyon doesn't just move faster than light, it moves backward in time. Let's break that down. In Einstein's theory, simultaneity is relative. That means two events that appear simultaneous to one observer might occur in a different order for another. When a particle moves faster than light, the math allows its signal to be received before it's sent, at least from some points of view. This gives rise to reverse causality. The effect can occur before the cause. In the case of tachyons, a message sent from point A to point B via a tachyon could arrive at point B before it was even sent. If that sounds like a paradox, it is. Imagine sending yourself a warning about a future mistake. You receive the message and avoid the mistake, but then you never need to send the warning. So where did the message come from? This is known as the grandfather paradox, a classic problem in time travel theories. For this reason, many physicists are deeply skeptical about the real-world existence of tachyons. If they could be used to send information into the past, it would fundamentally break the logic of reality. But some scientists argue that these paradoxes don't necessarily disprove tachyons. Instead, they suggest limits on what tachyons could do. Perhaps tachyons exist, but can never be used to transmit usable information. Or perhaps, even if they could, the universe has a built-in censorship mechanism, like the Novikov self-consistency principle, which states that any event caused by a time traveler or a tachyon signal must be consistent with the timeline that produced it. In other words, you can't change the past. You can only fulfill it. Some researchers have even proposed experimental setups to detect tachyons, such as Cherenkov radiation in vacuum or cosmic ray anomalies, but no conclusive evidence has emerged. Still, the idea lingers, especially in quantum mechanics. In some interpretations of quantum theory, such as the transactional interpretation, particles are thought to exchange waves forward and backward in time. This echoes tachyon behavior. In that model, a quantum event only occurs when a wave traveling forward in time meets a wave traveling backward. No causality is broken, but the interaction itself defies classical intuition. Could this be a hidden mechanism mediated by something tachyon-like? We don't know. But the mathematics of quantum field theory leaves the door open. In fact, Feynman diagrams, which physicists use to visualize particle interactions, often include particles traveling backward in time. These are interpreted as antiparticles moving forward. But again, it challenges our everyday sense of time. So let's take a step back. Why are physicists even entertaining such ideas? Because at the deepest levels of physics, time isn't what we think it is. Many equations, including those of quantum mechanics and general relativity, are time-symmetric. They don't care whether time moves forward or backward. It's only at the macroscopic scale, where entropy increases, that time seems to have a direction. This arrow of time may be emergent, not fundamental. If so, then reverse causality might not violate any fundamental law. It may simply be something we don't yet understand, a hidden symmetry of the cosmos, visible only under exotic conditions, like those involving tachyons. Some have speculated that entire regions of the universe, or other universes entirely, might operate under reverse time. In such a world, what we call future would be their past, and vice versa. If tachyons exist and can traverse both types of space-time, they might be the cosmic ambassadors, connecting timelines, bridging cause and effect in ways we cannot yet comprehend. And maybe, just maybe, our inability to detect tachyons isn't because they're fictional. Maybe it's because they're not bound by our direction of time. They could already be here, influencing events in subtle ways, before we even know to look for them. In the end, the real question isn't just, can tachyons exist? But rather, can we accept a universe where the future can reach back into the past? If that answer is yes, then we are on the verge of a new physics, one that shatters our deepest assumptions about time, fate, and causality itself. Einstein gave us a cosmic speed limit, the speed of light, approximately 299,792 kilometers per second. No object with mass can reach or exceed it. It's not just fast, it's the boundary that shapes our universe's structure. But what if something doesn't just break that rule? It was never bound by it to begin with? That's where tachyons enter the conversation. Unlike photons, which travel exactly at the speed of light, or particles with mass, which travel below it, tachyons would exist only above the speed limit. In fact, tachyons can't even slow down to light speed. They exist in a separate regime altogether. This flips our understanding of physics upside down. Because according to the equations of special relativity, as an object approaches the speed of light, its mass approaches infinity, and it would require infinite energy to go faster. But the same equations allow for imaginary mass when speed is greater than light, and that's exactly the mathematical signature of a tachyon. Physicists call this space-like motion, trajectories that lie outside the light cone of relativity. This means a tachyon's world line cannot be connected to ours through any slower than light interaction. But here's the twist. The math doesn't break. It just becomes stranger. Instead of being disallowed by Einstein's equations, tachyons are a legitimate mathematical solution, one that lies on the other side of the light-speed barrier. So why haven't we seen one? The problem lies in measurement. Tachyons, if they exist, would behave unlike any known particle. They would gain speed by losing energy and slow down by gaining energy, the exact opposite of normal matter. This inverse relationship makes them unstable in our observable framework. They might emit energy indefinitely, a process that some physicists argue would cause them to instantly decay or vanish from normal space-time. But others disagree. They propose that tachyons could form a hidden sector of physics, completely decoupled from standard particles. Like dark matter or dark energy, tachyons may interact only through gravity or quantum fields, making them invisible to all current detectors. Some theorists even speculate that the neutrino, a nearly massless particle, could have tachyon-like properties under certain conditions. In 2011, the Opera experiment in Italy created global headlines when it appeared to detect neutrinos arriving faster than light. For a brief moment, it looked like Einstein had been overturned. But within weeks, a faulty fiber optic cable was discovered, and the results were retracted. Still, the incident reminded the world that faster-than-light anomalies are worth investigating. If tachyons exist, they could explain more than just speed. They might unlock the mystery of quantum entanglement, where particles separated by vast distances appear to affect one another instantly. This non-locality has baffled scientists since the Einstein-Podolsky-Rosen paradox in 1935. While quantum mechanics accepts entanglement as fundamental, no one really knows how the information is shared. Could tachyons, unobservable but ever-present, be the missing link? Could they transmit correlations at superluminal speeds while staying hidden from our detectors? This wouldn't allow faster-than-light communication, since the outcomes are inherently random. But it could still tie together different parts of reality in a deeper, invisible way. Of course, this opens the door to speculation. Science fiction has long embraced tachyons as messengers from the future, as the engine for time travel, as the key to interstellar communication. But modern physics treats them with caution. In most quantum field theories, tachyons appear only temporarily, as signals of vacuum instability. In this view, they aren't real particles, but flags that a field is about to shift into a new state. Yet in some Lorentz-violating models, theories that allow small departures from Einstein's symmetry rules, real tachyons might still exist. They wouldn't violate causality in those frameworks because time, space, and information flow differently there. In fact, in the context of the emergent gravity hypothesis, where space-time itself is not fundamental but arises from deeper quantum networks, tachyons might behave like excitations in a more abstract structure, like ripples on a lattice of information. From that perspective, the speed of light is not a cosmic limit, but an emergent property. And tachyons may simply live above the layer we can see. Think of them like ocean waves that exist far below the surface, detectable only by indirect ripples in the deep. In this way, the tachyon becomes more than a particle. It becomes a conceptual bridge, connecting Einstein's rigid spacetime with a more fluid quantum foundation. A whisper that says, there may be more than one kind of reality. And as our tools evolve, as we push further into quantum computing, gravitational wave astronomy, and deep field cosmology, we may one day glimpse evidence of that hidden domain. A place where particles outrun light, time folds in strange directions, and causality flows like a river with forks unseen. Until then, the tachyon remains both a mystery and a muse, an invitation to think faster than light. What if we could send a message to the past? A warning, a whisper, a signal? What if the future had already tried to contact us, and we just didn't recognize it? Welcome to one of the most radical possibilities in physics, tachyon communication. In theory, tachyons are particles that travel faster than light, and by extension, could travel backward in time. This creates a tantalizing idea. Use them to send information into the past. But the implications are staggering. Let's unpack how it might work, and why it terrifies physicists. In special relativity, if a signal travels faster than light, then under some reference frames it can arrive before it was sent. That means you could send a tachyon-based message from point A to point B. And at point B, the message arrives before it was ever transmitted. A closed causal loop is formed. If such loops can exist, they raise all kinds of time travel paradoxes, especially when it comes to information. Let's imagine a simple experiment. A scientist discovers the method to generate a tachyon pulse. She programs the system to send a signal if a specific result occurs in her lab. But what happens if she receives the signal before she even starts the experiment? Would that affect how she proceeds? Would she change the result? This is the heart of the information paradox. Where did the information originally come from? Who is the sender? And who is the receiver? It creates what scientists call a causal paradox, where the cause and effect are so intertwined that it's unclear which came first. In logic, this is unacceptable. In physics, even worse. But not everyone rules it out. In fact, in the 1970s and 1980s, serious physicists, including E.C.G. Sudarshan and Gerald Feinberg, considered theoretical frameworks in which tachyons could transmit information. To preserve consistency, some of them proposed rules, such as, tachyon signals must be random or non-interfering. Only closed loops are allowed if they don't result in contradictions. A fixed frame of reference might prevent paradoxes. Another approach is the Novikov self-consistency principle, which suggests that any action taken to change the past was always part of history, meaning the paradox is resolved because the loop is self-contained. You received the message because you were always going to. It's fate, but dressed in equations. In science fiction, tachyon communication is often used as a plot device for reverse time broadcasting. Warnings from the future. Interstellar messages beating the speed of light. Quantum computers pinging their earlier states. One famous example is the movie Déjà Vu, where an experimental surveillance system based on tachyon physics allows law enforcement to observe the past and eventually try to change it. But could this ever be real? Let's explore some obstacles. Energy requirements. The generation of a controlled tachyon pulse would likely require exotic energy configurations, perhaps at Planck scale energies far beyond current technology. Detection issues. Tachyons wouldn't behave like photons or particles we can measure. They might only interact through gravity or higher dimensional fields. Signal stability. Because tachyons gain speed by losing energy, transmitting a consistent, structured message could be impossible. Cosmic censorship. The universe might inherently prevent such paradoxes from occurring. Like quantum uncertainty, it may bury contradictions beneath randomness. Even so, some physicists believe that quantum entanglement could one day be tied to tachyon-like interactions. Imagine this. two entangled particles separated by light years. A tachyon interaction tweaks one and retrocausally affects the state of the other, not by sending a readable message, but by changing the probabilities of outcomes. It's not classical communication, but it's influence. And that's enough to change how we think about information and time. Interestingly, there are also proposals in quantum cryptography to test for hypothetical faster-than-light correlations. Though no conclusive evidence has ever been found, these experiments push the boundaries of what's testable. Some even wonder whether tachyons could be used in interdimensional communication. If other branes or timelines exist, could tachyon flows cross them? This blends with theories of multiverse physics, where different regions of the universe operate under different physical laws. Maybe tachyons drift freely between them, acting as bridges between realities. It's wild speculation, but based on real math. Still, there's one central truth we keep returning to. Information defines reality. If tachyons can manipulate information across time, they challenge our most sacred principle, causality. And maybe that's the point. Maybe the universe isn't a straight line. Maybe it's a network of timelines, where information flows both forward and backward, and the tachyon is the thread connecting them. Until we find hard evidence, tachyon communication remains forbidden science. But like all taboos, it speaks to something deep, human, and universal. The desire to speak across time, to reach backward and change, or reach forward and hope. More than 95% of the universe is invisible. We can't see it, we can't touch it, but we know it's there, from the way galaxies rotate, from how light bends through space, and from the accelerating expansion of the cosmos. We've given it names, dark matter and dark energy. But what if these mysterious forces are more than just unknown substances? What if they're manifestations of something far stranger, something like tachyons? Let's explore the possibility that tachyons, faster-than-light particles with imaginary mass, may help explain the darkest parts of our universe. First, a quick review. Dark matter makes up about 27% of the universe. It doesn't emit light or energy, but exerts gravity, keeping galaxies together when visible matter isn't enough. Dark energy accounts for about 68%, and it's pushing the universe apart, accelerating cosmic expansion in ways we still don't fully understand. So where do tachyons come in? Some theoretical physicists have proposed that tachyon fields, scalar fields containing faster-than-light components, could behave like dark energy. Here's how. In string theory and quantum field theory, when a field is unstable, it can roll down toward a stable vacuum. This rolling process releases energy and can act like a negative pressure field. That's exactly what dark energy seems to be. One popular model is the tachyonic scalar field, a slowly evolving field with negative pressure. As it decays, it drives expansion, mimicking the effects of a cosmological constant. This idea gained traction in the early 2000s, especially as observations from WMAP and Planck confirmed that dark energy behaves like a constant but might be slightly dynamic. Tachyon fields fit the bill. They can be stable, slow-rolling, and still contribute to accelerated expansion, all without violating known laws of physics, as long as the tachyons don't transmit information or cause paradoxes. But that's just dark energy. What about dark matter? That's trickier. Dark matter clumps together. It forms halos around galaxies. It behaves like invisible mass. Tachyons, on the other hand, are repulsive. Their energy-momentum tensor behaves oppositely to normal matter. So, are they completely unrelated? Not necessarily. Some hybrid models propose that tachyon condensates, collections of tachyonic fields that decay into stable states, may leave behind topological defects or exotic remnants that interact only gravitationally. These remnants might behave like dark matter, clumping, bending light, and forming structure. In brain world scenarios, where our universe is a membrane in a higher dimensional space, tachyonic interactions between brains could lead to localized energy zones that resemble dark matter. Even more radically, some physicists propose that dark matter and dark energy aren't separate things, but two phases of the same underlying tachyonic field, acting differently in different cosmic regions. In this unified dark sector model, the tachyon field evolves over time. In some places, it creates gravitational attraction, dark matter-like effects. In others, it causes repulsion, dark energy-like acceleration. This would be an elegant solution. One field, two behaviors, governed by local conditions. Of course, it's still theoretical, but it gets even stranger. In certain string-inspired cosmologies, the entire early universe may have been dominated by tachyonic energy. This pre-Big Bang phase, sometimes called the tachyon-dominated era, would be a universe driven by instability, rolling down the vacuum landscape until it settled into the universe we see now. If true, then dark energy is not just a present phenomenon, but a lingering echo of our origin story. The slow decay of that early tachyon field may still be ongoing, pushing space outward. That would mean we're not just surrounded by tachyon energy, we are its consequence. But how could we ever know? Detecting tachyons directly is next to impossible. They don't interact via the strong, weak, or electromagnetic forces. But we might infer them indirectly. For example, unexplained fluctuations in dark energy's behavior over time, variations in the cosmic microwave background that can't be explained by standard inflation, tiny gravitational lensing anomalies inconsistent with particle dark matter. If these patterns match the predictions of tachyon field models, it could be the smoking gun. Furthermore, experiments like the Euclid telescope, the Vera C. Rubin Observatory, and the James Webb Space Telescope are gathering unprecedented data about dark energy and dark matter distribution. We may soon discover inconsistencies, cracks in the standard model that point toward a new kind of field, a tachyonic fingerprint hidden in the cosmic code. Of course, many scientists are skeptical. Some argue that invoking tachyons overcomplicates the issue, that simpler explanations will do. And they may be right. But if we want to truly unify cosmology with quantum theory and string physics, we may need to embrace the strange. Tachyons may not be figments of science fiction. They may be the foundation of dark reality, not particles that violate causality, but fields that shape everything we see and don't see. So the next time you look up at the stars and wonder what's holding them together, or what's pushing galaxies apart, remember, it might not be matter or energy in any traditional sense. It might be tachyons, whispering from beyond the light. What if time doesn't flow the same way everywhere? What if, somewhere, somehow, another universe is playing in reverse? It's not just a science fiction idea. Some cosmologists propose that the Big Bang didn't just create our universe. It created a mirror twin, a universe where time runs backward. And connecting these two realms? Maybe something faster than light. Maybe something like a tachyon. Let's dive into one of the most compelling ideas in theoretical physics, that our universe is one half of a symmetric time structure, and tachyons may be the link. Here's how it works. According to the laws of physics, many equations are time-symmetric. That means they don't care whether time runs forward or backward. Quantum mechanics, electromagnetism, even general relativity, they all work the same way in reverse. So why does time seem to move forward? The answer is entropy, the increase of disorder, which gives us the arrow of time. But what if the universe is balanced? What if, for every moment of increasing entropy here, there is decreasing entropy elsewhere? That's the basis of the Janus cosmological model, named after the two-faced Roman god of beginnings and endings. It proposes that the Big Bang launched two universes, one expanding in positive time, the other in negative time. From our perspective, the mirror universe is running backward. From theirs, we are. Now here's where tachyons get interesting. Tachyons are hypothetical particles that move faster than light. But more importantly, they also appear to move backward in time. In our universe, they would look like particles coming from the future. But in a time-reversed universe, they would behave normally, moving forward. So, what if tachyons are natural inhabitants of this mirror universe? What if they bleed across the border, influencing both sides of time's arrow? This could explain why they're so hard to detect. They may not belong fully to our universe, but exist in between. A bridge between forward time and backward time reality. In this view, tachyons are inter-universal messengers. They don't just move faster than light. They move across time domains. And just like a gravitational wave crosses space, a tachyon might ripple between temporal fabrics. Could they carry information across the divide? Could they be responsible for the subtle quantum fluctuations we observe, like virtual particles appearing from nowhere? Some speculative physicists have proposed that quantum entanglement may arise from interactions between opposite time universes. Two particles in our universe become linked because they are actually entangled across time. Their counterparts in the reverse-flowing universe mirror their behavior. If so, tachyons may serve as the threads stitching space-time together across temporal symmetry. This also has implications for dark matter and dark energy, as discussed in Segment 8. Maybe what we perceive as gravitational effects with no source are simply reflections of mass energy from the time-reversed universe, mirrored into our own via tachyonic coupling. Even more radical is the idea that we ourselves might be quantum reflections, that every atom in our body is part of a larger time-symmetric structure, and we are just half of the whole. In such a universe, death in one time flow could be birth in another. Collapse in one direction could be creation in the other. And time itself is not a one-way street, but a mirror hallway. But what kind of physics would allow tachyons to move between such realities? One theory is that the light barrier is not a boundary, but a portal. For subluminal, slower-than-light particles like us, crossing that portal is impossible. But tachyons, which exist only beyond the speed of light, might freely oscillate between forward time and reverse time domains. In Feynman diagrams, antiparticles are often drawn as particles traveling backward in time. Could this be more than metaphor? Could antimatter itself be a tachyonic echo of a time-reverse domain? Some scientists have proposed that matter and antimatter are symmetric across time, and that what we see as rare antimatter may simply be ordinary matter from the mirror side. If this is true, then the asymmetry problem, why the universe has more matter than antimatter, might be an illusion. It's balanced, just not in our direction of time. All of this leads to a profound possibility. The tachyons don't break causality, they complete it. They might resolve paradoxes by weaving both sides of the cosmic story into one larger, self-consistent picture. In this picture, free will, determinism, past, future, they all dissolve. There is only symmetry. Two universes, one expanding from the Big Bang into the future, the other expanding from the Big Bang into the past. Tachyons pass between them, unseen, faster than light, linking fate to origin. Until we can prove it, it remains theory. But perhaps, just perhaps, every time we measure a quantum event, glimpse a cosmic mystery, or feel a strange synchronicity, we are brushing against the mirror. And in that reflection, the tachyon smiles. We began this journey with a question. What if something can outrun light? But now we're asking something much deeper. What if reality itself is more fluid, more recursive, more conscious than we thought? Tachyons, those elusive faster-than-light messengers, have taken us through time loops, mirror universes, unstable vacuums, and the dark side of cosmology. But what if their true significance isn't about speed, but about meaning? Here's a radical idea, that tachyons are not particles, they're processes. Not matter, but intent. They may represent the universe's way of correcting itself, of updating its own state across time. Think of reality as a cosmic algorithm. It's not fixed, it's recursive, constantly feeding back on itself, refining the present based on future states. In this framework, tachyons are not glitches. They are the feedback signals. They loop backward through space-time to ensure self-consistency. If this sounds like science fiction, consider this. In quantum mechanics, the transactional interpretation already proposes that particles communicate via advanced, future to past, and retarded, past to future. A quantum event only occurs when both waves complete a handshake, a loop across time. In this picture, causality isn't broken, it's completed. And what if that principle applies to the entire cosmos? What if the universe sends itself information across time, not just to fulfill physical laws, but to preserve narrative structure? We often think of the cosmos as cold, mechanical, indifferent. But what if it's more like a story, one that wants to be told in full, without contradiction? Tachyons could be the punctuation marks, retroactive corrections that make the timeline coherent. They appear in moments of quantum uncertainty, in black holes, in field instability, not to disrupt reality, but to align it. In this view, every quantum fluctuation isn't random. It's responsive. The future informs the present. The present anchors the past. And time is not a one-way river, but a self-writing script. This reframes our understanding of everything. Maybe entanglement is not spooky action, but intentional correspondence. Maybe dark energy is not a mystery, but the universe pulling itself into the next chapter. Maybe the Big Bang wasn't a beginning, but a call and response event, a tachyonic resonance across two timelines. Here's a poetic thought. The universe may not be a machine. It may be a mind, not a conscious being in the human sense, but a self-referencing system capable of learning, adjusting, and expressing. In such a cosmos, tachyons are like neurons firing between moments in time. They allow the system to become aware of itself, not linearly, but holistically. So what does that mean for us? For you, the listener, sitting in your timeline, looking backward and forward? It means this: you are not a passive observer. You are a node in the loop. Every decision, every perception, every dream you've ever had feeds into the grand recursive architecture of space-time. You might not send tachyon signals, but your choices could be echoes of them, ripples from a future you haven't reached yet. And perhaps the strangest possibility of all is that every time we ask, "What if?" we're responding to something already sent, some whisper from beyond causality, a tachyonic question planted deep in the quantum soil of the cosmos. As we close this series, let's not just marvel at tachyons as abstract math. Let's see them as clues, signs that the universe is more alive, more interconnected, more narrative than we dared believe. And maybe, just maybe, that's the real speed limit that's waiting to be broken. Not the speed of light, but the speed of understanding. It's larger than Mercury. It has its own magnetic field. And beneath its frozen surface may lie a vast, global ocean. Welcome to Ganymede, the largest moon in the solar system, and one of Jupiter's most fascinating and mysterious worlds. In this episode of Infinity Beyond, we dive deep into the science of this icy giant and uncover why it's fast becoming a top target in the search for alien oceans. Discovered by Galileo in 1610, Ganymede is the third of the Galilean moons and the largest natural satellite in our entire solar system, measuring over 5,200 kilometers in diameter. That's 8% larger than Mercury, though only about half as massive. What makes Ganymede so remarkable is that it behaves like a planet, despite being a moon. It has a layered interior, with an iron-rich core, a rocky mantle, and a thick outer shell of water ice. But here's where it gets really exciting. Beneath that icy crust lies a subsurface ocean, possibly 100 kilometers deep, sandwiched between layers of ice. This ocean is thought to be salty, electrically conductive, and may contain more water than all of Earth's oceans combined. If confirmed, it would make Ganymede a leading candidate in the search for extraterrestrial life. But Ganymede's uniqueness doesn't stop there. Unlike any other moon, Ganymede has its own magnetic field, discovered by NASA's Galileo spacecraft in the 1990s. This field is likely generated by a liquid iron or molten saltwater layer within the core. It interacts with Jupiter's powerful magnetosphere, creating stunning auroras in Ganymede's thin atmosphere, shimmering belts of light that glow near its poles. These auroras also help scientists study the internal structure of Ganymede. When the auroras rock back and forth under Jupiter's magnetic influence, researchers can model how the moon's interior conducts electricity, supporting the theory of a deep, global ocean. The surface of Ganymede is a blend of two terrains: dark, older regions heavily cratered from impacts; lighter, younger areas marked by grooves and ridges. These features suggest tectonic processes where surface ice cracked and shifted, possibly due to subsurface movement or tidal heating from Jupiter. One theory proposes that the ice shell periodically shifts or overturns, cycling fresh material to the surface. This could explain the relative youth of some surface features and supports the idea of cryovolcanism, icy eruptions that release slush or water. Ganymede also has a very thin atmosphere, composed mostly of oxygen, but it's far too tenuous to breathe. However, it's another piece of the puzzle that makes this moon resemble a frozen Earth on a grand scale. To explore Ganymede's secrets, the European Space Agency, ESA, is preparing the JUICE mission, short for Jupiter Icy Moons Explorer. Launching in the 2020s, JUICE will conduct multiple flybys of Ganymede before entering orbit around it, becoming the first spacecraft to ever orbit a moon other than our own. Its mission: to map the surface, probe the ocean beneath, study the magnetic field, and assess the potential for habitability. JUICE will carry radar instruments capable of penetrating up to 9 kilometers into the ice, allowing scientists to detect subsurface features. It will also analyze surface composition, temperature, and structure, helping determine whether Ganymede could support microbial life. But Ganymede isn't just important on its own. It also plays a critical role in the broader Jovian system. Its gravitational interaction with neighboring moons, Europa and Io, creates orbital resonances that help maintain tidal heating. This interconnected dance keeps the inner Jovian system geologically active. Ganymede also influences the space weather environment around Jupiter. Its magnetic field carves out a mini magnetosphere within Jupiter's massive one, shaping how particles flow and move. Could Ganymede host life beneath its icy shell? It's still unknown, but all the ingredients are there: liquid water, energy from tidal heating, complex chemistry. Whether it's a microbial ecosystem near the core or frozen organic molecules awaiting discovery, Ganymede may hold answers to how common life is in the universe. In the far future, this moon might even be a destination for exploration or habitation. Its large size, stable geology, and potential water sources make it a tempting base for long-term missions. In the next episode of Infinity Beyond, we'll descend into the volcanic fury of Io, Jupiter's most chaotic moon, and the most volcanically active place in the solar system. Imagine a world where the ground never stops shaking, the sky rains molten sulfur, and volcanoes constantly erupt, not for days or weeks, but for billions of years. Welcome to Io, the innermost of Jupiter's Galilean moons, and the most volcanically active object in the entire solar system. In this episode of Infinity Beyond, we plunge into the chaotic, fire-breathing surface of Io, where extreme tidal forces create a hellscape of lava lakes, explosive plumes, and ever-changing terrain. Discovered by Galileo in 1610, Io is roughly the same size as our moon, but it's anything but lifeless. With over 400 active volcanoes, Io's surface is constantly reshaped by flowing lava and towering eruptions. Some plumes reach up to 500 kilometers, 300 miles, into space, higher than the International Space Station orbits Earth. But what fuels this planetary inferno? The answer is tidal heating. Io orbits just 421,000 kilometers from Jupiter and is locked in a gravitational tug-of-war with its siblings Europa and Ganymede. This three-body resonance keeps Io's orbit slightly elliptical, meaning its distance from Jupiter is constantly changing. As Io swings closer and farther from the gas giant, Jupiter's immense gravity stretches and compresses its interior, generating tremendous friction and heat. This internal heating melts rock into magma, fueling volcanic activity on an unimaginable scale. Unlike Earth, where heat comes from radioactive decay and leftover formation energy, Io is externally powered, heated from the outside in. The result? A tortured molten landscape. The surface is a canvas of sulfur, silicates, and volcanic pits. Bright yellow plains, red and black lava flows, and circular calderas form a bizarre alien palette. One of Io's most famous volcanoes is Loki Patera, a massive lava lake over 200 kilometers wide. Its eruptions are so regular, they've been used to study volcanic cycles across the solar system. NASA's Galileo mission captured images of lava fountains, glowing hotspots, and moving flows, changing from one flyby to the next. Some lava temperatures reach 2,900 days, hotter than most Earth eruptions. Io also interacts directly with Jupiter's magnetosphere. As charged particles bombard its surface, Io ejects material into space, creating a torus of plasma that encircles Jupiter. This plasma torus not only glows in ultraviolet light, but also contributes to Jupiter's auroras, making Io a key player in the planet's electromagnetic environment. Volcanic gases escaping from Io, mainly sulfur dioxide, form a thin atmosphere that quickly escapes into space or freezes back onto the surface. There are even signs of transient auroras above Io's poles due to this interaction. Despite its activity, Io is likely uninhabitable. Its surface is far too hot, radioactive, and geologically unstable to support life as we know it. Unlike Europa or Ganymede, it lacks a protective shell or stable ocean beneath. Yet Io is still critically important. Studying it helps us understand tidal heating as an energy source, planet-moon interactions, volcanism beyond Earth, how moons shape planetary magnetospheres. These lessons extend beyond our solar system. Many exoplanets orbit close to their stars, experiencing similar tidal stress. Io offers a natural laboratory to model these extreme environments. Future missions like NASA's Europa Clipper and ESA's JUICE won't fly directly over Io, but will continue observing its volcanic activity from afar. There are proposals for dedicated Io orbiters or landers in the future, perhaps with infrared imagers, seismometers, or even sample return goals. Capturing a sample of Io's lava would be revolutionary, giving us direct evidence of extraterrestrial volcanism. For now, Io stands as a world in constant motion, a fiery contrast to the icy moons around it. Its eruptions continue to shape Jupiter's space environment, reminding us that the solar system is still alive, dynamic, violent, and ever-changing. In the next segment of Infinity Beyond, we zoom out to explore Jupiter's role as a gas giant, its internal structure, layers of hydrogen and helium, and whether it truly has a core at all. From the swirling storms on its surface to the crushing depths within, Jupiter is a planet of layers, pressure, and mystery. But what lies at its center? Does the gas giant have a solid core, or is its heart made of something stranger? In this episode of Infinity Beyond, we journey deep inside Jupiter to uncover what scientists believe lies beneath the clouds, through its atmosphere, and into its possible core. Jupiter is composed mostly of hydrogen, about 90%, and helium, around 10%, similar to the Sun. But unlike the Sun, Jupiter never became massive enough to ignite nuclear fusion. As we descend into Jupiter's layers, the pressure and temperature rise dramatically. Let's break it down. Layer 1. The atmosphere. Jupiter's upper atmosphere is composed of clouds of ammonia ice, ammonium hydrosulfide, and water, arranged in alternating zones and belts. These form the planet's striped appearance and drive powerful jet streams and storms like the Great Red Spot. Descending beneath the clouds, we encounter a region where the gas becomes denser and hotter. Temperatures exceed hundreds of degrees Celsius, and pressures reach dozens of Earth atmospheres. Layer 2. Liquid hydrogen. Deeper still, the hydrogen gas compresses into a liquid form. Jupiter has no solid surface. Instead, the transition from atmosphere to interior is gradual. Here, hydrogen behaves more like a dense metallic fluid. In fact, the boundary between gas and liquid isn't clearly defined. Layer 3. Metallic hydrogen. At about 1.4 million kilometers from the center, under pressures over 3 million times Earth's atmosphere, hydrogen becomes metallic. In this state, electrons move freely like in a metal, allowing this layer to conduct electricity and generate Jupiter's powerful magnetic field, the largest in the solar system. This metallic hydrogen layer may span over 40% of Jupiter's radius, and it's likely rotating differentially, meaning the inner regions spin at different rates than the outer layers. Deepest layer, the core, maybe. And finally, at the center of Jupiter lies the big question: is there a solid core? Earlier models suggested Jupiter formed around a rocky or icy core, roughly 10 to 20 times Earth's mass, which then accreted gas from the solar nebula. But new data from NASA's Juno spacecraft, which measures gravitational variations with extraordinary precision, suggests that the core may not be solid at all. Instead, Jupiter might have a diluted core, a large region where heavy elements are mixed with lighter elements like hydrogen and helium. This mixing could have occurred due to impacts during Jupiter's early formation, like a collision with a massive planetary embryo, disrupting a previously solid core. Juno's data reveals that heavy elements are spread out over a large volume, possibly up to half of Jupiter's radius. So instead of a compact rocky center, Jupiter may have a fuzzy, partially dissolved heart, a strange state of matter where rock, metal, and hydrogen coexist under immense pressure. This revelation has shaken planetary science. It means our models of gas giant formation may need to be updated. Jupiter may not be a perfect example of a two-layer planet, but something far more complex. Understanding Jupiter's interior also helps us study exoplanets, especially the many gas giants we've discovered orbiting distant stars. Do they all have cores? Are they diluted too? Some gas giants, like hot Jupiters, may be even puffier, with extended atmospheres and complex interiors. Jupiter serves as our baseline, the one we can study up close. There's also a cosmic connection. Jupiter's mass is just below the threshold needed to become a brown dwarf, a failed star. Had it formed just 80 times more massive, it could have ignited fusion and lit up as a second sun. So, the mystery of its core isn't just about structure, it's about Jupiter's identity, planet or almost star. Future missions may reveal even more. Juno continues to map Jupiter's gravity and magnetic field with increasing detail. A follow-up mission, possibly with probes or orbiters closer to the center, could test the diluted core theory further. For now, Jupiter remains a world of speculation, a gas giant with a stormy surface, a liquid metal mantle, and perhaps a dissolving heart. In the next segment of Infinity Beyond, we'll look outward again, this time to Jupiter's gravitational reach. How far does it extend? And how does it shape the outer solar system, including asteroids, Trojans, and comets? When we think about power in the solar system, we think about the Sun. But in terms of gravitational dominance, besides the Sun, nothing comes close to Jupiter. In this episode of Infinity Beyond, we explore the immense gravitational reach of the gas giant and how it sculpts the orbits of asteroids, shepherds comets, and protects, or endangers, life on Earth. Jupiter contains over 70% of the non-solar mass in our solar system. That's more than twice the combined mass of all the other planets, moons, and asteroids put together. This mass gives Jupiter incredible gravitational influence, and this influence stretches well beyond its orbit. Let's break down how. Asteroids and the asteroid belt. Jupiter's gravitational pull is responsible for shaping the asteroid belt between Mars and Jupiter. In this region, objects orbit the Sun, but certain orbits are unstable due to orbital resonances with Jupiter. These resonances create Kirkwood gaps, empty zones in the asteroid belt where Jupiter's gravity clears out material by nudging objects into new orbits, often sending them flying into the inner solar system. That might sound dangerous, but it also helped prevent the belt from forming a planet. Without Jupiter, we might have had a Mars-sized world between Earth and Jupiter, with unpredictable consequences for Earth's orbit. Trojan asteroids, Jupiter's bodyguards. Jupiter also hosts Trojan asteroids, two massive swarms of objects locked into stable Lagrange points, 60 degrees ahead and behind the planet in its orbit. These space rocks are gravitationally balanced between Jupiter and the Sun. Some are over 200 kilometers wide, and many are likely remnants from the early solar system. NASA's Lucy mission is currently on its way to explore these Trojans, offering insight into the formation of gas giants and the building blocks of planets. Planetary migration and orbital shaping. In its early days, Jupiter may have migrated inward and then outward, a theory known as the Grand Tack hypothesis. This tack, like a sailboat changing course, would have disturbed the protoplanetary disk, influencing how and where the other planets formed. Some simulations suggest that without this migration, Earth might never have formed, or could have been a much larger, ocean-covered planet, more like a super-Earth. Comets and the Oort cloud Jupiter also has a profound effect on long-period comets that enter the inner solar system from the Oort cloud. Its gravity can do three things: capture them as temporary moons, eject them entirely from the solar system, redirect them into orbits that cross Earth's path. In this way, Jupiter acts as both a cosmic shield and slingshot. It protects Earth by absorbing or deflecting dangerous objects, but can also send them our way. A famous example is comet Shoemaker-Levy 9, which broke apart and slammed into Jupiter in 1990. The impact created fireballs, larger than Earth's diameter, a reminder of what Jupiter can intercept. Earth's orbital stability. Jupiter's mass also contributes to the long-term stability of Earth's orbit. It acts as a kind of gravitational anchor, balancing the solar system. Without Jupiter, the orbits of Mars, Earth, and even Venus could become more erratic over millions of years, potentially causing orbital instabilities or increased collisions. In fact, studies have shown that Jupiter's position helps dampen chaotic motion from the outer solar system, allowing Earth to remain in the habitable zone with relatively stable seasons and climate. Influence beyond the solar system. The study of Jupiter-like exoplanets has exploded in recent years. Many large gas giants have been found orbiting other stars, often much closer to their host stars than Jupiter is to the Sun. These so-called hot Jupiters are believed to have migrated inward over time, sometimes destroying or ejecting smaller terrestrial planets. Jupiter's position in our solar system may be unusually favorable for life, far enough out to protect the inner worlds, but close enough to maintain order in the planetary orbits. Jupiter, then, is not just a planet. It's a gravitational architect, a cosmic gatekeeper, and a planetary protector, and sometimes a potential threat. In our next episode of Infinity Beyond, we'll step even farther out into the region of the Trojan swarms and explore what NASA's Lucy spacecraft hopes to find in this ancient debris field. They've silently orbited the Sun for over 4 billion years, untouched, unchanged, and largely unexplored. In this episode of Infinity Beyond, we dive into the mysterious world of Jupiter's Trojan asteroids, ancient remnants from the formation of the solar system, and explore how NASA's Lucy mission will finally visit these forgotten fossils of time. So what are Trojan asteroids? Unlike the main asteroid belt, which lies between Mars and Jupiter, Trojan asteroids share Jupiter's orbit around the Sun. They cluster in 2 swarms, one 60 degrees ahead of Jupiter, called the L4 swarm, 160 degrees behind Jupiter, the L5 swarm. These regions are known as Lagrange points, places where the combined gravitational pull of Jupiter and the Sun allows smaller objects to remain stable over time. There are over 10,000 known Trojans, and possibly hundreds of thousands more yet to be discovered. Some are dozens of kilometers wide. What makes them special is that they are believed to be primordial leftovers from the birth of the solar system, similar in age and composition to Kuiper belt objects. Unlike main belt asteroids, which have been heavily modified by collisions and solar radiation, Trojans have been preserved in cold storage, relatively undisturbed. Studying them could answer some of the biggest questions in planetary science. How did the planets form? What materials existed in the early solar system? Were organic compounds present in these ancient rocks? That's where NASA's Lucy mission comes in. Launched in 2021, Lucy is the first spacecraft ever sent to explore the Trojan asteroids. Over the course of 12 years, it will visit 8 different asteroids, including 7 Trojans and 1 main belt asteroid as a warm-up. Lucy's trajectory is a cosmic dance, flying past Earth 3 times to gain speed and looping out to reach both the L4 and L5 swarms. The mission is named after the famous hominid fossil Lucy, because these asteroids are expected to be fossils of the solar system's past. The spacecraft is equipped with a high-resolution camera, LLORI, a color imager and infrared spectrometer, LRALPH, a thermal infrared spectrometer, LTES. These instruments will allow Lucy to map surface geology, analyze composition, detect minerals, and even measure surface temperatures. Among the key targets are Eurybates, a dark, carbon-rich object thought to be similar to primitive solar system material, Polymele, Lucas, and Orus, irregularly shaped bodies with unique rotation rates, Patroclus and Menetrius, a binary Trojan system, 2 objects orbiting each other in tandem. The diversity among these targets is already surprising. Some Trojans are reddish, while others are gray. Some seem rocky, others icy. This could indicate that they originated from different regions of the solar nebula, and were later captured by Jupiter's gravity. If true, it would suggest that Jupiter acted as a collector of solar system material, gathering samples from across the disk and storing them in stable orbital locations. By analyzing these asteroids, Lucy may uncover clues about how giant planets migrated, how the early solar system was mixed, and how water and organics were distributed across space. The mission will also help us prepare for future asteroid mining or deflection technologies, as understanding asteroid structure and composition is key to both. But Lucy isn't just about science. It's also an incredible engineering feat. The spacecraft uses solar panels that span over 7 meters, allowing it to power itself even at Jupiter's distance from the Sun. Its orbit is one of the most complex NASA has ever attempted, a multi-loop trajectory that visits multiple targets without needing to slow down or land. After its final flyby, Lucy will continue orbiting the Sun indefinitely, perhaps becoming a future relic itself, silently traveling among the asteroids it was sent to study. The significance of this mission cannot be overstated. Just as Lucy the hominid helped us understand our biological origins, Lucy the spacecraft may help us understand our cosmic ones. In the next episode of Infinity Beyond, we'll return to Jupiter itself to explore how the gas giant formed and why its early journey across the solar system may have determined the very existence of Earth. Earth, before Mars, and before the rings of Saturn, there was Jupiter. In this episode of Infinity Beyond, we travel 4.6 billion years into the past to uncover the violent, chaotic birth of Jupiter, and how this one planet's formation may have determined everything from the existence of Earth to the placement of asteroids. Jupiter is thought to be the first planet to form after the Sun ignited. Within just a few million years of the solar system's birth, Jupiter began accumulating mass. According to the widely accepted core accretion model, Jupiter started as a solid core made of ice and rock, around 10 to 20 times the mass of Earth. Once this core reached critical mass, it began pulling in the hydrogen and helium gas that remained in the solar nebula, the giant cloud of dust and gas left over from the Sun's formation. This process happened fast, within 1 to 10 million years. If it had taken any longer, the gas would have dispersed, and Jupiter might never have grown to its present size. But why is this important? Because Jupiter's formation didn't just create a planet. It triggered a cascade of gravitational effects that shaped the rest of the solar system, clearing the neighborhood. As Jupiter grew, its powerful gravity began sweeping up or scattering nearby debris. It prevented other large planets from forming between it and the Sun, which is why the asteroid belt never coalesced into a planet. Jupiter also began flinging leftover planetesimals outward, helping to form the Kuiper belt and seeding the Oort cloud, the Grand Tack hypothesis. One fascinating theory about Jupiter's early life is called the Grand Tack hypothesis. According to this idea, Jupiter initially migrated inward, perhaps as close as 1.5 AU from the Sun, near the current orbit of Mars. But before it could become a solar system wrecker, Saturn formed, and the two giants entered a gravitational resonance. Their mutual interaction caused them to tack, like a sailboat, and reverse course, migrating outward to their current positions. This inward-outward motion would have had massive consequences. It explains why Mars is smaller than expected. It explains the mixed composition of the asteroid belt, dry and icy bodies. It may have helped deliver water and organics to the early Earth. In short, Jupiter may have helped set the stage for life by both shaping planetary orbits and delivering essential ingredients, organic molecules, and delivery to Earth. As Jupiter scattered icy bodies inward, many of them may have carried carbon compounds, amino acids, and even water. These could have bombarded early Earth, delivering the raw materials for life. Without Jupiter's early gravitational chaos, Earth might have remained dry or never formed at all. Was Jupiter always alone? Recent studies suggest Jupiter may have once had a planetary sibling, a second gas giant that was later ejected from the solar system. This would explain some of the orbital anomalies seen in the outer planets. If true, it means the early solar system was even more violent and dynamic than previously imagined, a place of planetary billiards where only the strongest survived. What Jupiter tells us about other worlds. Studying how Jupiter formed helps us understand exoplanetary systems. Many solar systems discovered so far contain hot Jupiters, gas giants that orbit extremely close to their stars. These worlds likely migrated inward, possibly disrupting the development of rocky planets. Our Jupiter, however, stayed far enough out to allow Earth to form and evolve in peace. Some astronomers believe that a stable, distant gas giant may be a key requirement for habitability, shielding inner planets from comets and providing gravitational structure. Probing the past. NASA's Juno mission continues to gather clues about Jupiter's internal structure and gravity field. Its findings support the diluted core theory, where heavy elements are mixed deep into Jupiter's interior, possibly a result of a giant impact in its youth. Future missions, combined with simulations and lab experiments, may finally reveal exactly how and when Jupiter was born, and whether other systems follow similar patterns. For now, one thing is clear. Without Jupiter, the solar system would be a very different and possibly lifeless place. In the next episode of Infinity Beyond, we'll explore how scientists study the storms of Jupiter, including the technologies used to see through clouds, measure wind speeds, and track lightning on a planet hundreds of millions of kilometers away. Jupiter is over 700 million kilometers from Earth, a world of storms, radiation, and ever-shifting clouds. But how do we study it in such incredible detail? In this final episode of the Infinity Beyond Jupiter series, we reveal the tools, missions, and brilliant methods scientists use to explore a planet they can never touch, and the surprising technologies that let us see beneath its turbulent atmosphere. First, let's start with the challenge. Jupiter has no solid surface. Its surface is a dense layer of clouds composed of ammonia, ammonium hydrosulfide, and water, with cloud decks that extend hundreds of kilometers downward. These thick cloud layers block visible light and constantly swirl in chaotic patterns. Studying what's below the top layers requires specialized instruments that can peer through storms, orbiters, and flybys. Several spacecraft have visited Jupiter, each providing new ways to see the unseen. Pioneer 10 and 11, first spacecraft to fly by Jupiter in the 1970s. Voyager 1 and 2 provided detailed images of Jupiter's atmosphere and moons. Galileo Orbiter, 1995 to 2003. The first to orbit Jupiter and drop a probe into its atmosphere. Cassini and New Horizons used Jupiter for gravity assists and captured valuable data. Juno, 2016 present. Currently in orbit, providing the most detailed insights ever. Galileo's atmospheric probe, one of the most daring missions, was Galileo's atmospheric entry probe in 1995. It plunged into Jupiter's clouds, lasting 58 minutes before it was destroyed by pressure. In that short time, it measured temperature and pressure gradients, chemical composition, including water vapor, wind speeds over 600 km/h. These direct measurements validated and calibrated remote sensing instruments used today. Juno's suite of instruments. NASA's Juno spacecraft is a scientific marvel. In a highly elliptical orbit, it avoids Jupiter's deadly radiation belts while flying close to the cloud tops every 53 days. Key instruments on Juno include JunoCam, a visible light camera for public engagement and weather tracking, microwave radiometer, MWR, peers deep into the atmosphere to detect water, ammonia, and temperature profiles. Gravity. Science instrument. Uses Doppler shifts to map Jupiter's internal mass distribution and support the diluted core theory. Magnetometer. Measures Jupiter's enormous magnetic field with extreme precision. Jade and Jedi. Analyze particles and auroras. MWR in particular allows scientists to see hundreds of kilometers into the planet, revealing hidden weather patterns, vertical cloud structures, and ammonia cyclones invisible to optical cameras. Lightning and thunderstorms. Jupiter's atmosphere is incredibly dynamic. It contains thunderstorms bigger than Earth itself and lightning up to 10 times more powerful than our own. Juno has captured low-frequency radio bursts emitted by lightning deep within the clouds, helping scientists locate and analyze them. Interestingly, lightning on Jupiter is more common at the poles, unlike Earth's equatorial storms, possibly due to differences in vertical convection and cloud layer structure. Spectroscopy and Earth-based observations. While spacecraft provide direct data, Earth-based telescopes remain essential. Instruments like the Very Large Telescope, VLT, and James Webb Space Telescope, JWST, can use infrared spectroscopy to measure and atmospheric composition, cloud particle sizes, heat escaping from the planet. Even amateur astronomers contribute by tracking storms and auroras, helping coordinate with space missions in real time. Wind speeds and atmospheric modeling. Scientists measure wind speeds on Jupiter by tracking cloud features over time, including the Great Red Spot and smaller vortices. By comparing images taken hours or days apart, software can calculate movement rates and build models of jet streams, shear zones, and turbulent eddies. Juno has revealed multiple cyclones at the poles, arranged in hexagonal patterns, a surprise that's now being modeled in labs on Earth using fluid dynamics simulations. The future of Jupiter exploration. While Juno has extended its mission into 2025, future missions may go even deeper. Europa Clipper. Though focused on Jupiter's moon Europa, it will gather valuable data on Jupiter's magnetosphere and plasma environment. Proposed atmospheric balloons. Long-term floating probes could drift through Jupiter's skies like weather balloons, transmitting real-time data. Submillimeter and radio telescopes. Ground-based tech is evolving to study deeper layers with better resolution. Eventually, AI and machine learning may analyze Jupiter's weather systems faster than human scientists, tracking storm evolution and discovering unseen trends. Final thoughts. Jupiter is more than a gas giant. It's a cosmic laboratory. It challenges engineering. It pushes science. And it continues to surprise. With every orbit, every image, and every byte of data, we get closer to answering the grand question: how do giant planets work, and what do they tell us about the universe? Thank you for joining this 17-part journey through Jupiter. Subscribe to Infinity Beyond and continue exploring, because the universe is only just beginning to reveal its secrets.